Welcome to lesson 15. Before you can fully understand what maths is and what it's used for, you must have an awareness of both what can happen in a given situation and why. The why part is very important because it motivates you to concentrate on learning the what can happen part. As an example, consider this scenario. You want to have a fence built. You make a design using 2-metre sections. You ask a carpenter for a cost estimate. Now we have a focus on the situation total cost. This supplies the why. And it sets you thinking about relevant details. The carpenter says he calculates his costs on the basis of $250 and $100 for each section. He then asks a question. What do you think that question might be? Obviously, it's how long is the fence going to be? You reply 10 metres. He says $750. Is that the correct amount? In other words, can you duplicate how he arrived at that figure? The calculation is shown below. The total cost in dollars is $250 plus the $100 for each section. 10 metres, 5 sections. So this equation represents a total made up of a starting value and 5 increases. Each section increases the cost. Notice the structure is apparent in the word total. Mathematically, we are repeating a setting discussed in earlier lessons. We have a new application of our old maths. Think about the carpenter's reply for a moment. Why is the $250 given as a separate figure? It might be to cover the time spent ordering materials and arranging delivery. It could also involve time for clearing the construction site. It is common for quotations to involve what we call fixed costs separately from variable costs. What we're working with is shown below. The total $250 fixed and $100 units, a variable number of them. So our equation representing what is happening here is the total cost is $250 plus a number of $100 panels. Notice the N represents the number of sections. And our two variables in this equation are the total and the number of sections generating that total. We can investigate the type 1 aspect of this by generating a set of examples. These clearly indicate possibilities that can happen. So if we have one panel, $350 for the total cost. 2 panels, 450. 3 panels, 550. And we can make other convenient examples as well. We can use those values to produce a quick overview of what is happening. In other words, make a type 3 illustration, picture, graph, whatever you like to call it. Here the number of panels is the input. The output is the cost of the fence that results. If we have 2 panels in the fence, 2 panels generates a cost. If we have 3 panels, and as we said, 3 panels cost $550 for the fence. By continuing the line joining those dots, we can estimate the value of any fence we want. Now, any type 2 maths involves an unknown, such as how long a fence can I get for $950? We can represent this by an equation and then solve it. So the equation is 250 for the fixed costs plus an unknown amount for the fence itself makes a total of $950. Only one unknown, we can calculate its value. We have to shift the 250 away from the unknown, reverse its processing, generates a conclusion. Now, what is the relevance of the 700? What is the relevance of what we have calculated? It's the cost of the fence panels. And that's not exactly what we wanted to know. We wanted to know how long is the fence. So we must convert this figure, this 700, the way we do it, $700 is the cost of a number of $100 panels. By shifting the 100, instead of multiplying, it will divide. We generate the value 7. This number is relevant to our scenario, but it's still not the answer to the question, how long is the fence? So we must convert the 7. We convert it based on the nature of the relationship. Total length is related to the number of panels. The total length is generated by multiplying the length of each section by the number of sections. Therefore, we have the calculation. The missing length is the individual length multiplied by what we now know we need 7 panels. So the length of the fence will be 14 metres. Is this how you thought about it? Many people do, and it's quite valid reasoning. But what we have here is actually 3 calculations with logical breaks and restarts between them. The answer to one calculation is the input for the next. Each stage is brief, only 3 lines. There's a clear logical link between the stages, and that's based on the relevance of the value generated by the previous calculation. Mathematics is being used here, but has it been used efficiently? No, this calculation isn't very efficient. Now, being aware of general mathematical structures allows us to make things easier and have less chance of errors. Where we had 3 separate calculations and there was a chance of an error in each, we have a high chance of an error overall. But being aware of general mathematical structures allows us to state that all 3 sections of the calculation can be collapsed together into one calculation. One calculation will be quicker and have less chance of an error. We will attempt to do this by making the equation that follows. Now, we know generally a result is always what you start with plus allow for the changes. So in this case, the total cost is the starting cost plus the number of sections by the cost of each section. This is the subtotal for the variable cost. This is the fixed cost. So based on that, our calculation would be $950 is $250 plus $100 for each of the sections. Trying to isolate our unknown, shift the 250, it will subtract. We haven't isolated the unknown yet, so shift the 100, it will divide. This leads to the conclusion that the missing part of our equation is 7. Now, we got to the 7 more directly than we did previously, but as we've said, it's not the length, and so it's not the solution to the problem. Did you notice what we did wrong? We did not have length mentioned in the equation representing the scenario. So we'll make a new attempt. Beginning with the same statement we had previously, total cost, fixed cost, variable cost, we have to adjust that to mention length. Now, the number of sections we need is the total length of the fence divided by the length of each section. So have a look at the replacement I'm making here. So our calculation will be based on the equation 950 is 250 plus the number of sections expressed in length times the cost of a section. It's the same statement that we had before, but it's expressed in terms of the length. So, isolating the length that we want, shift the 250, it subtracts. Now shift the 100, it divides. Exactly the same as before. But now we shift the 2 and it multiplies. So in one calculation, we go directly from a general statement, which is adapted to what we want, to calculating what we want to know. So we were able to calculate the length in one calculation. We had to make sure that what we wanted to know was mentioned in the equation that formed the basis of our understanding of the problem. Now make a note of the following. The total cost of all sections can be calculated by multiplying the number of sections by the section's cost. But we had to express the number of sections in terms of their length. in this particular case. So type 1, type 2 and type 3 maths is relevant here. They supply what you need in order to understand what is happening in a real life situation. You can bring that understanding to a problem because you have generated it in advance. You understand the problem before you even see the problem. Each new predicament is now viewed as a modification of a previously understood mathematical structure. As I've said many times, we have 3 types of maths activity which can apply in any scenario. Type 1 is always encountered first because it gives us relevant examples. These give us an awareness about what we might have to deal with. It is often advantageous to then move directly to type 3. This is because the role of type 3 maths is to give a visual overview, which should enhance understanding. And the type 1 examples we generated are the illustrations input. One of the most useful aspects of any type 3 illustration is it provides a two-way view of the relationship. We can read graphs as either input to output or output to input. In the latter case, it can facilitate the inverse processing required for type 2 calculations. Consulting illustrations, or graphs as we call them, can be quicker than using a calculator. The calculator can give greater precision, but consulting the graph can give you greater speed. Also, a graph can indicate the significance of the result compared to other options. So the whole calculation could have been avoided if the carpenter had already drawn a graph. Here we have the appropriate graph. Number of panels, cost. The question is, how much fence can I get for $950? Begin with 950, move to the part of the graph that's appropriate, and find your answer. Now, this axis can be labelled as number of panels, as we did before, or it can be labelled as distance, length of the fence. Notice 1 panel, 2 metres, 3 panels, 6 metres, 7 panels, 14 metres. So the graph holds the answers in advance. Notice how the horizontal axis had 2 scales. We will meet that again in later cases. I'll see you in the next lesson. We'll extend these ideas then.